I include a simple problem here that I have noticed presents difficulties for my students when I include it on a test or homework. The elevator problem. Imagine you have an elevator that is moving with an acceleration that is upwards. Now, this doesn't mean that the actual motion or speed, velocity of the elevator is upwards. What this means is that if the elevator was moving upwards, then it's speeding up. And that if the elevator is moving downwards, then it's slowing down. So that is what it means to have the acceleration pointing upwards. Imagine you place a scale on the ground here inside the elevator and you step inside. How much will that scale read for your mass? So let me put the details here. We'll have a 70-kilogram person standing on a scale in an elevator that is moving with an upward acceleration of 0.2 g. What does the scale read? Before we get to the solution, let's make sure we understand what does the scale usually read. So what is the scale reading? Let me pull the person and the scale outside the elevator and place them on a platform that does not move with any acceleration. So in this case, I will have gravity pointing downwards, a normal force to account for the interaction between the feet of the person and the scale. That vector has to point upwards. And it is this vector, the magnitude of that vector, that stands for the interaction between the feet and the scale, that is actually related to the scale reading. So let's see how much that is. We're going to start with Newton's second law, or specifically with the y components here of the forces and the acceleration. The acceleration, of course, is 0, so the right-hand side will be 0, and on the left-hand side, I will have minus mg for the y component of the gravitational acceleration and plus Fn. I call the y component here the normal force Fn, and that has to be equal to 0. So I see that the normal force will be equal to m times g. And in terms of reading, that eventually will lead me to the mass. But please note that the scale never reads the gravitational force. It reads the pressure between your feet and how hard your feet are pressed against itself, and then it infers what the gravitational force must be and what your mass is. The second thing that I want to mention here is that most of the scales, even though they read newtons, eventually the display gives you grams or kilograms, unless you live in the United States or a country that uses the imperial system for units, and then you'll end up with pounds. My advice is to stay away from pounds if you can, when you're solving physics problems. If you're solving a problem like that on a test, ask your instructor or your teaching assistant, TA, for clarification whether those pounds refer to mass or to force. I have seen them used both in both situations for mass and pounds, and it's really confusing. Which I personally think is totally unnecessary in physics. But anyway, beside the point, my advice is stick to the metric unit, units of newtons, and everything will be absolutely clear. We know that if we have newtons, that will be force, and if we get kilograms or grams, that will be a mass. So with that, let's go to the reading of the scale. The actual display takes the force in newtons and divides it by 9.8, which is the acceleration due to gravity, to give us something of the nature of the mass. In this particular example, since the Fn is going to be mg, once I cancel g, I end up with the exact mass of the person. So you see, it's a clever way to get to the mass, even though the scale could never really directly measure the gravitational force or figure out our mass, but it has a clever way to go about through Newton's laws and assumptions for the balance of forces to get to the mass. In different situations, any of those assumptions might actually break, and we might not be allowed to use them. So that will lead to actually wrong reading, which is the case of this problem. Let's see how it plays out for the elevator. In the elevator, the gravitational force again will be downwards, just as before, with components 0 and minus mg. The normal force, just as before, will be with components 0 and plus Fn, pointing upward. Remember, the normal force stands for the interaction between your feet and the scale. What is different in the elevator problem is that the elevator has an acceleration, and consequently the person inside the elevator being moved together with the elevator will also have an acceleration. So and that acceleration, let me write the components here, will have components 0 and plus a. By the way, if you're solving this problem with an elevator moving with an acceleration downwards, you just change the component here from plus a to minus a and proceed with the steps that I'm about to show you. The solution is identical. We start with Newton's second law, or specifically with the relationship for the y components. We're going to have minus mg plus Fn has to be equal to the m times the y component of the acceleration, which in this case for upward acceleration is going to be plus ma. So immediately I see the difference. The normal force, or the force that accounts for the interaction between the feet and the scale, is not going to be equal to mg as before, but is going to be mg plus ma. In plain words, what this means is that the normal force has to push upward to cancel the gravity or to offset the gravity that is pulling you down. And in addition to push, it has to push even further, a little bit more, to account for that extra acceleration in the upward direction. So that is the extra term ma that the normal force needs to exceed the gravity by. So that things can work out the way they set up in the problem. So with that, I can factor out m, and I see that the normal force will be m times the sum of the g and a. The reading itself on the display of the scale will be the normal force divided by g, or it will be m times g plus a over g. I'm ready now to put the given information from the problem into my answer. The reading of the scale will be m times g plus the acceleration, which the problem tells me it's going to be 0.2 g, or 20% of g, and everything has to be divided by g. When I factor out g from the parentheses, g actually can cancel out, and I see that the reading will be different from the correct reading. In fact, the scale will be reading 1.2 times the mass of the person. For a 70-kilogram person, that turns out to be 84 kilograms, which is completely in alignment with our own personal experience. For anybody who has been in an elevator, when the elevator begins to move upwards, or an elevator that is actually slowing down towards the ground floor, we all feel that we feel heavier, but it's really what we actually referring to is that we feel the pressure between our feet and the floor to be higher than normal. One more subtle point here I'd like to make is that even though I said the scale reads the normal force, technically the scale physically reads the force F, which is the force with which the feet of the person push against the scale surface. So the scale reads the forces that exerted on itself on the scale. That will be a force, a vector downwards. Here I have marked it in green. I called it F. And it applies, that force F applies to the scale. That is where usually we have some springs or it could be like a crystal in the scale, depending on what sensitive scale and what you're measuring. But there's some mechanism inside the scale there that tells you what is the force applied on the scale. Nothing really changes. It's kind of like a subtlety that helps the whole understanding, and actually be aware of how all Newton's laws are always present and entwined together in our solutions, even though we focus more on the second law, simply because we have Newton's third law that tells us that the interaction between the feet and the scale will show up in two vectors. One vector on the person when we draw the free body diagram for the person, and that will be the normal force, the blue vector, and one vector that I will draw normally on the free body diagram for the scale. I didn't draw it before because I didn't have to. I focused only on the person, and when you draw vectors, you draw only the vectors that are applied to that object. So the green vector would be actually on a separate diagram if I wanted to analyze what are the forces acting on the scale.